Section: Introduction. In this section, we discuss how we can effectively transfer knowledge from a larger teacher model to a smaller student model, a method known as knowledge distillation. This approach has proven successful in creating more efficient models across various applications. As large language models, LLMs, become more widely used, we have also applied knowledge distillation to enhance smaller LLMs. We focus on distribution matching, where we learn the output distribution from the teacher model. Specifically, we work in an offline Logit setting, meaning we pre-compute and store the teacher's output before training the student. This method has several benefits for LLMs. The larger teacher model only needs to be run once, and we can use the saved outputs to train multiple smaller models. Additionally, we can perform teacher inference on less expensive computing resources, allowing us to train the student on smaller clusters and reducing the memory requirements of the teacher. This setup also makes it easier to conduct smaller-scale experiments without the constant burden of the teacher model. While this approach is often used for post-training or dataset generation, applying it to pre-training is more complex. Knowledge distillation requires storing the detailed soft targets, or teacher probabilities, which can be challenging due to the large vocabulary size of modern LLMs. For instance, storing all probabilities for a model like Llama 3 could require an impractical amount of storage. To address this, sparse knowledge distillation methods store only a selected subset of logits from the teacher's distribution. However, these methods can still lead to performance drops if too few logits are stored. Through theoretical proofs and empirical analysis, we demonstrate that the performance decline in top K methods arises from two main issues. They provide a biased estimate of the teacher's probability distribution and do not adequately expose the tail of the distribution to the student. This results in the student learning an inaccurate version of the teacher's distribution. We propose a solution using importance sampling to randomly select from the teacher's distribution, which allows us to provide an unbiased estimate, maintain gradient preservation, and reduce the need for extensive teacher inference while keeping model performance comparable to full distillation with minimal storage. In our exploration of top K knowledge distillation, we note that previous studies have suggested using a subsampled version of the teacher distribution. The simplest method is to select only the top probability values from the teacher, known as top KKD. Theoretically, choosing the top tokens minimizes error for a single token. We can also combine this with top P, which adjusts the number of tokens based on a fixed probability mass. To evaluate top KKD, we pre-train several Llama-style student models while varying the number of probabilities used. We train on web data using a well-prepared teacher model and compare the performance of our student models against those trained with only cross-entropy loss and those using the full teacher distribution. Our findings show that top K training generally lags behind the performance of full KD. When using a small number of top K tokens, the student model performs worse than with cross-entropy loss alone. It is only after using a sufficient number of tokens that we see performance approaching that of full KD. Although top P allows for fewer tokens, the performance still falls short of full KD. We also assess the expected calibration error, ECE, of these models, as calibration is closely linked to performance. Despite our teacher model being well calibrated, we find that models trained with top K are significantly miscalibrated, and this miscalibration worsens as we reduce the number of tokens. In contrast, models trained with cross-entropy and full KD maintain good calibration, consistent with previous observations. Section Summary. In this section, we discuss the application of knowledge distillation, KD, in training smaller language models by leveraging pre-computed logits from a larger teacher model, focusing on the challenges and limitations of top K methods. We propose an improved approach using importance sampling to provide unbiased estimates of the teacher's probability distribution, which enhances model performance while reducing storage requirements and eliminating the need for extensive teacher inference. Section: Top KKD Analysis. In this section, we highlight key issues with top K methods. First, when we only keep the top K values from the teacher's distribution, the probabilities of these top tokens become inflated because they need to be adjusted to sum to 1. We demonstrate this with a synthetic distribution that follows a ZIF distribution, showing similar biases found in earlier studies. Next, when we apply KL divergence loss with top K knowledge distillation, KD, the probabilities for non-top K tokens drop to 0. This occurs even without normalizing the top K probabilities. As a result, the student model learns an exaggerated version of the teacher's probabilities, with the leftover probability distributed among the top K tokens. This leads to the student being overly confident in the top K tokens and less confident in others, which we observe during top K pre-training for large language models, causing calibration errors that worsen as we reduce the number of tokens. We also see this calibration error in a simple synthetic classification task, where we train a small multilayer perceptron to classify random points in a high-dimensional space. Here, top KKD results in overconfident models, while other methods like cross-entropy and full KD show much better calibration. The same issue arises when we train a toy ResNet model on the CIFAR 100 dataset, indicating that we cannot use KL divergence loss on the top K target distribution without addressing the remaining probabilities. Moreover, merely addressing the inflated teacher probabilities does not fully restore performance. Unlike full KD, which uses the complete distribution, top KKD ignores the tail information, which is vital for model performance. Rare tokens that fall into the tail of the teacher distribution are discarded, leading to a weaker training signal compared to cross-entropy training. Even though the tail has a small probability mass, it contains valuable information that needs to be learned. We then propose several empirical solutions to these issues and apply them to top KKD, presenting the results in a table. One straightforward approach is label smoothing, where we distribute the leftover probability equally among all classes. While this corrects the calibration error, it significantly reduces performance compared to top KKD, as real-world token probabilities are not uniformly distributed. Another method involves creating a ghost token that captures the probabilities of non-top K tokens for both the teacher and student. We compute the loss for the top K tokens and the ghost token, allowing the top K tokens to receive gradients similar to full KD, while the remaining tokens get gradients based on student confidence. This improves both loss and calibration, but performance still lags behind full KD, indicating that explicit supervision for the tail is crucial. Lastly, we consider a simple solution where we use the ground truth for the residual probability, which we call naive fix. This method adjusts the target token's probability to ensure the total sums to 1, leading to better alignment with the actual target. While this significantly enhances performance and calibration, it still requires more tokens to match Folkdy's performance. Overall, the methods we discussed either provide biased estimates of the teacher's probability distribution or lack sufficient supervision for the tail. Section Summary. In this section, we identify key issues with top K knowledge distillation, KD, including the upscaling of teacher probabilities and the loss of tail information, which leads to overconfidence in top tokens and poor performance on rare tokens. We propose several empirical solutions, such as label smoothing and the introduction of a ghost token, but emphasize that explicit supervision of the tail is crucial for bridging the performance gap compared to full KD. Section: Random Sampling KD. In this section, we discuss random sampling knowledge distillation, KD. We utilize importance sampling to get unbiased estimates of a function by sampling from a different proposal distribution and adjusting the samples using the likelihood ratio. If our proposal distribution is not valid at any point, the estimate becomes biased. While any non-zero proposal can yield an unbiased estimate under certain conditions, the one with the lowest variance takes a specific form. Based on this, we choose a particular proposal distribution, where the sampling temperature is a key factor. We sample tokens from this distribution for a set number of rounds, assigning a likelihood ratio to each token, which we then normalize to create a target probability distribution. To compare fairly with top KKD methods, we keep the average number of unique tokens equal to k. We find that the performance remains stable across different sampling rounds and unique token counts, so we simplify our experiments by using a fixed temperature. Our method demonstrates accurate estimation of the teacher distribution, achieving perfect calibration in various tasks, including synthetic classification and LLM pre-training. Compared to other KD methods, models trained with random sampling KD show better calibration, and using fewer tokens does not negatively impact this calibration. We also show that random sampling maintains expected gradients at the logits, similar to full KD. Empirically, we measure gradients from a model trained with full KD and find that those from random sampling are very similar, with only a small angular difference. In contrast, top K methods exhibit larger differences in gradients. While top K methods yield the least error for a single token, they provide biased estimates of the teacher distribution, leading to the observed gradient discrepancies. Our method remains unbiased, but it is essential for the estimator to have low variance for better approximation of the teacher distribution. We note that using a uniform proposal across the vocabulary can lead to noisy estimates, causing training issues. We find that using 62 tokens is sufficient for our experiments. We compare the speed of our method against full KD and CE, finding that our caching implementation is significantly faster than full KD and only slightly slower than CE due to the need to compute loss over the entire vocabulary. We evaluate our method using various metrics, including LM loss, expected calibration error, acceptance rates in speculative decoding, and zero-shot NLU and NLG scores. In our small-scale results, we train llama-style models with a 4B teacher and find that our method performs comparably to full KD while using fewer tokens. Interestingly, as we increase the number of unique tokens, random sampling shows slightly better performance than full KD, suggesting that perturbing teacher logits may enhance knowledge distillation. Section Summary. In this section, we explore the random sampling knowledge distillation (KD) method, which utilizes important sampling to provide unbiased estimates of teacher distributions while maintaining low variance, leading to better gradient preservation compared to top K methods. Our empirical results demonstrate that random sampling KD achieves similar performance and calibration to full KD, while being significantly faster and requiring fewer tokens. Section: Effect of longer training. In this section, we extend the training of our student model to 7 billion tokens, which is significantly more than the chinchilla optimal amount. We find that our model performs similarly to full KD in both speculative decoding and zero-shot natural language understanding scores. To validate our results with open-source large language models on public datasets, we train student models using the Llama 4 billion to 8 billion model on the FineWeb Edu dataset. Initially, we train a 4 billion Llama-style student with 7 billion tokens. We observe a larger loss gap between top K knowledge distillation and full KD in this scenario. However, the student trained with random sampling KD, which uses 62 unique tokens, shows comparable loss, calibration, and speculative decoding acceptance rates, along with significantly better performance in downstream tasks and instruction following. The improvements we see in smaller experiments continue to hold for larger models with extended training. We also assess the 4 billion models using Llama 3.174 billion instruct as a judge on 5 instruction following tasks. The student model trained with random sampling KD outperforms all other methods across these tasks. Additionally, we experiment with different student sizes, training models of 7 million, 6 million, 13 billion, and 4 billion, all using Llama 4 billion to 8 billion as the teacher, for a total of 76 times the model size in tokens. We consistently see improved performance in zero-shot downstream evaluations using random sampling KD as the student model size increases. While similar trends have been noted for top K pre-training, previous reports indicate a drop in performance for smaller student models, which we believe may be due to the issues with top KKD that we discuss. We also explore other methods proposed in the literature to enhance full KD performance, showing that these can be applied to random sampling KD as well. We combine Kullback-Leibler divergence and cross-entropy losses during training, where the final loss is a weighted sum of these two. Some prior works use different training modes for tokens based on the teacher's confidence, where higher scores indicate easier tokens to learn. We implement a similar adaptive method in our random sampling KD by classifying tokens in a batch as easy or hard, based on their target confidence. Hard tokens are trained with a higher learning rate compared to easy tokens, while maintaining a constant average learning rate. We train 6 million models using a 4 billion teacher, varying the cross-entropy weight and learning rate ratio, and report the percentage of cross-entropy to full KD. Our results show that these methods allow random sampling KD to outperform full KD. The best model is achieved with a cross-entropy weight of 79 and a learning rate ratio of 80. We also apply this approach to train a 4 billion student with an 8 billion teacher for 7 billion tokens, further improving random sampling KD in terms of language model loss, speculative acceptance rate, and zero-shot NLU scores. However, we note that this model does not improve significantly after instruction tuning. We suspect that increasing the weight of hard examples in the learning rate may overly emphasize the tail of the distribution, leading to higher calibration error and underconfidence in predictions. While this enhances pre-training scores, it negatively affects downstream fine-tuning. Finally, we discuss how selecting the optimal sampling temperature can reduce variance in probability estimates, balancing the sampling of varied tokens with accurate estimates for higher probability tokens. Although the optimal temperature depends on the distribution shape, our numerical simulations indicate that a specific temperature results in the lowest variance. The post-training performance of these models is comparable, and for simplicity, we choose a specific proposal distribution in our work. Section Summary. In this section, we demonstrate that extending training of the student model and employing random sampling KD leads to performance comparable to full KD across various tasks and model sizes. We also explore adaptive learning rates for different token difficulties, which further enhance the effectiveness of random sampling KD, although we note potential drawbacks in downstream fine-tuning due to calibration issues. Section: Effect of Adapting Teacher. In this section, we discuss the effect of adapting the teacher model. We found that when a student is trained on a data distribution that differs from the teacher's pre-training data, it is beneficial to first adapt the teacher by fine-tuning it on the new data for a short period. We observed this ourselves when training a 6 million parameter student on FineWeb Edu data using the Llama model with 8 billion parameters as the teacher. Using the original teacher model resulted in only a slight improvement, but after adapting the teacher for 1 billion tokens, the performance increased significantly. Next, we explored different loss or divergence functions by training 6 million parameter students with the 8 billion parameter Llama teacher for 68 billion tokens. Some previous studies have found that alternative objectives like reverse KL divergence and mean squared error can be better, while others have reported the opposite. In our findings, we noted that the standard forward KL divergence outperformed the other objectives. Regarding related work, knowledge distillation has been frequently used to enhance smaller language models. Many studies focus on using teacher models for generating or filtering datasets. Our approach is somewhat complementary, as we concentrate on distilling the teacher model's outputs regardless of the pre-training data source. Similar to our work, some studies have stored the top teacher probabilities from a language model for training smaller students. They noted that using the top tokens can lead to overly confident students, which they addressed with temperature scaling. By sampling from the teacher's distribution, our method provides a systematic way to achieve a well-calibrated student model. While they also found miscalibration in their teacher models, we discovered that both our 4 billion and 8 billion parameter Llama teachers are well calibrated since they are not instruction tuned. Our work is closely related to others that have observed improvements in student model performance through distillation. However, they stored a large number of teacher logits, which is impractical for modern language models. We successfully reduced this to 62 logits in our study. Additionally, we examined caching teacher logits in knowledge distillation during the pre-training of language models, utilizing a combination of top K and top P sampling. They concluded that forward KL divergence is superior, and adding cross-entropy loss enhances distillation, especially when scaling model size and pre-training data. However, they noted a decline in performance for smaller students, as we demonstrated in our findings. Our method addresses this issue by achieving results comparable to full knowledge distillation with a much sparser set of tokens.